So when two or more objects, please consider recording the lecture too if you want. That also can help you if you want. Because I'm pretty much saying what I'm writing anyway. Two or more objects come together or come into contact. We call this event a collision. This event can be deliberate or accidental. So normally when we talk about a collision, we talk about a car accident or something, and obviously we hope those are accidental events. But of course, in science and engineering and even in physics, there's lots of events where collisions occur by design. So we have to watch that we don't let our common language trespass into the technical language, and once again, that's a challenge for us, but that's just how it is. There are two basic types. Now I'm going to give you a hand-waving kind of thinking man's version of it, then we'll go into a technical definition. So an elastic collision the bonds are stretched but not broken. And the objects bounce off each other. And the main thing that I'll stress in a minute is that the amount of compression and recoil is often incredibly slight. Because objects are fairly rigid. So this compression is often slight. But just like we said last year, this compression occurs in all accidents. There is no such thing in our day-to-day of an object that does not compress a little bit, including the floor when you drop something on it. It may be nanometers, but it's not zero. So compression due to impact however minuscule is not zero. Okay? So we have to stress that, and that's another thing that appears like it's zero because it's so small, but again, it's not perceptible to the eye. But remember in our force times displacement equation that the work done, if the displacement is zero, then you have infinite force, which doesn't exist. So, so we have to remember that it may be small, but it's there. And if you go into materials physics, there's a tremendous amount you learn about how compressibility and stress, where parts of things compress and other parts don't, and some of the most expensive software is written for things like that. An inelastic collision results in some chemical bonds being broken directly due to the impact. As a result, the rebound / bounce effect is modified. Now, that being said, this can be really important. So car accidents are a good example. Cars have major damage to them. Okay, if the car is just an elastic collision, the car you wouldn't be able to know it was in an accident. And but it's an interesting point because, say, for car accidents, and we learned this last year, we want to increase the displacement so that the force of impact is reduced to assist the occupants in surviving the accident. So work is equal to integral of FDS. So if S increases, force decreases. So cars are designed with crumple zones with deliberate and so that an impact will result in greater survivability. So, unfortunately, your parents have sort of happened. I'm not going to be very happy. The car gets crumpled slightly, and to fix that costs a lot of money, and that usually results in a bunch of grumbling at the dinner table. But the reason the car is delicate is that if you do hit something, coupled with the airbags, the chances the car is your armor, all right, and you fall out of the car, as it happened in the past. When people were ejected from the car, they would either fly in the air and hit something that was very solid, which was bad for them, or the car would land on top of them, which was really bad for them. By keeping you in the car with the seat belts, that restraint system gives you the armor, the protection of the car, and then the car destroys itself while the passenger compartment is more or less kept intact. Now there's of course limits. If you're irresponsible as how you're driving, you get some really bad luck, there's a limit to anything. But it is a tremendously more survivable accident. In the 1950s and early 60s, when seatbelts didn't exist, and the cars were much more rigid, and the bonnet of the car and the fenders were quite stiff, you could sit on them, and they didn't deflect or anything. What would happen is that you see the car after an accident, and sometimes the car didn't look that bad, but it had hit something and bounced off of it, and the people had hit the windshield, and they were dead, and the car had really, didn't look too bad. Now sometimes, of course, if it's bad enough, they'll look bad no matter what. So this was all invented into the 1970s, 80s, and beyond to make these cars far more rigid. So if you're underneath the car sometime, you'll see that the frame of the car is complicated. It's not just two I-beams going the length of the car, which might be a simple way to build it. It's very complicated, and this is all pre-designed to bend and flex if something happens that we don't plan. If you're driving, do everything you can to avoid a head-on collision. Sideswipe, put it in the ditch, whatever, because it gives you more time to slow down, more time to deal with the eventualities than if you hit head-on. That's of course going to really minimize. First, it's going to massively increase the energy of the collision, and second, it's going to minimize the displacement. And this is often when the worst things happen. The same thing is hitting a feature like a hydro pole. Try to avoid those things. Go into the ditch and slide along, and or hit a fence post or something which is nowhere near as substantial as these light stands are. Try to control it as best you can. But the main thing is If you drive defensively and leave adequate space between you and whoever else, it gives you more time to react to bad things. And then hopefully that none of them will ever happen. But there's nothing you can do better than buy time. And that's where the separation is greater. Whatever the separation you're giving, give more. If someone cuts in front of you, that will just slowly let that grow again. No one's going to arrest you for that. I just want to make sure I'm recording. I believe I am. I just don't want to do it wrong. Hang on for a second, please. Okay. So there's some interesting things, and like I said, we just look at this from whether the object is deformed permanently, so therefore clearly chemical bonds have been broken, or if it's basically the same, like a squishy ball, you bounce it and it looks the same. Those are the basic definitions there. There is some energy lost in the bouncing ball because it doesn't come quite as high as they like to teach you in math class, but that's a secondary point. So, technically speaking, an elastic collision is the kinetic energy is conserved. So Tn, Ti equals Tf. And this is, of course, for the system, not for individual particles. Now, in real truth, because when you drop your ball and it bounces back up again, there's going to be some vibration and some heat generated in the molecules and the chemical bonds, within the bonds that don't break, obviously. So you're not going to have total conservation of energy here because it just doesn't work that way. But for a first approximation, we will assume that it does when we talk about collisions that are considered to be elastic. And so it's a fairly involved calculation because you have two conditions to satisfy. So the first one is conservation of momentum, and then conservation of kinetic energy. And they both have to be met for elastic collisions. Now, to derive the equations for this would take too long for what it's worth, so we won't. And then an inelastic collision now, in real world, there is a degree of inelasticity, but they don't generally get to that. I don't think when I was in university they even told us about that, but it is on some simulations. We won't bother with it, but basically what you can say, if it's inelastic, you can assume that the final velocity of both particles is the same. So the two particles coupled together somehow. A bullet went into a piece of wood and stayed there, and then the piece of wood went somewhere else. Two cars come along, or like a train cars, and they catch, and then they go down the track. That's the kind of thing you're looking for from a standpoint of an inelastic collision. It's not the same as destruction of bonds, like we talk about car accidents, because you can't imagine how complicated that would be to analyze. So the inelastic collisions we're talking about here are different kinds of ones, where the coupling of the cars has absorbed the differences in the velocities. Okay? Or if the bullet goes into the wood, the friction of the wood has done work on the bullet, and so there's a change there. Okay? So what we're going to look at is the two particles will couple in some manner. And this can be, certainly 1D for sure. Okay? Generally, the 2D collisions we'll do will be elastic type, because you've got deflections and stuff, and so then the coupling is not really practical. We do not deal with any rotation in our collisions. Clearly, when things are hitting as glancing collisions, you're going to impart torque. And so I'm not going to deal with that theoretically, but in the simulation, it is part of the arithmetic. Let's just see what's going on here. No, it looks like it's still down. Okay, whatever. Now in inelastic collisions, you still have conservation of momentum. So you just lose this one, but there's enough usually here because you do have that, know that the velocities are, final velocities couple. So that gives you an extra condition which allows you to be able to solve it. If you remember last year, we had in a case where with the mass was, so we had a moving target, stationary target, and we had, this is a 1D collision for now. So then we had something like V2, V1F, and V2F. And I gave you an expression for those. And they're all based on V1I, because the only velocity we can work with is the initial velocity of the hockey puck, if you will, coming in, because the other one's sitting still. And we used Van Dummel's law of extremes to verify this. So if the object's coming in, it's really big, and it hits the other one, it's going to keep on going. And it's going to maintain its speed pretty much. So we have M1 plus over M1 plus M2. So if the object coming in is small, then it will not have much, it will stop. And if I've done this right, somehow I don't think I have. A second here, M1 minus M2. Yeah, that sounds right. I'm testing my memory here deliberately to see. Okay. Let's just check and see if I'm anywhere near correct here. Yes, how about that? Okay. And then we're going to have 2 M1 over M1 plus M2. And this is done, so this is the 1D case. If we go to 2D, so it's still not a 2D, pardon me, but a moving target. Same logic otherwise. Then we have V1F, but now we have to consider the initial velocity of both objects, and so we do them in reverse. The nice part is the pattern here makes some sense for once. So we're going to have M1 minus M2 over M1 plus M2 V1I plus 2 M1, or is it M2? M2, yeah. Good feeling. Over M1 plus M2 V2I, and then the other one, V2F, will equal right, okay, see. So 2 M1 over M1 plus M2 V1I, there we go, plus now when you do this term you have to reverse these ones, so this is going to be M2 minus M1 over M1 plus M2 V2I. So the second term here looks like this one, only this is M2, and here we reverse the top. Other than that, I believe that's it. Yes. So if we have a 1D collision with a moving target, you just add the extra term, and now the logic is basically the same. Okay? So that could easily happen. We could have objects come together. You could have an object receding and another one chasing it and catching it, that kind of thing. Lots of stuff like that could happen. And then, of course, the glancing collisions is a bit of a different thinking. And then I'm going to come back to the microscopic aspect of this, but I'll cover this first. You already kind of know a bit about it. So 2D glancing, target at rest, and then in star, we do not consider the imparting of rotation. Furthermore, we also do not consider slippage. Of the surfaces as they impact. So let's just say a word or two about this without writing it down. If two, let me just make a little diagram. If two objects come together here at this point, their initial contact, all this happens really quickly, but within that, there'll be initial contact where the force, the normal force connecting the two of them is not enough, and they'll slip, okay? The frictional force will not be high enough to resist what's going on here. As the collision continues, the impact will generally create an adequate normal force, and then that's when rotation is imparted. And then ultimately, when they leave each other, there'll be a point where that no longer occurs. So all this happens in 100th of a second or whatever. And you might say, well, it really doesn't matter, but it does matter because everything's just happening faster. But don't think it's not happening, okay? So we're not going to deal in this class, and I don't remember it happening in first year either, dealing with the nuances here of imparting rotation. Now, you might put your hand up in first year after the professor deals with this. Sir, would those particles not cause rotation, and how do you handle that? And then you might get, well, we'll do that in second year. I would expect most first year courses right now would not do this. But anyway, it's a good question because it shows you're interested in it. And then if he asks you further, you could say, well, last year we wrote a simulation on this, we modeled it. Because that's an option in the collision simulation, is to model rotation of the two objects when they hit as a Inelastic collision when both are moving. And you verify that on some kind of online simulator, wherever it is. Okay, so this one here, we use conservation of momentum, but in each axis separately. So as we already talked about last year in grade 11, one of the problems in 2D is unfortunately some students have resisted this notion of components and will try to do with magnitude and angles. And it's absolutely critical in this case to take components of these particles. So basically what we're saying here is that the momentum is conserved in X and Y independently. So, for example, if a puck comes along and hits one like this, the initial momentum in the Y direction was, right, 0. So therefore, when you're finished, you're going to have a resulting Y momentum of 0. And that generally is accounted for when you have this type of thing. This momentum is acting, the Y component is acting downward, this is acting upward. Depending on the mass ratios and so forth, you will get a situation where the Y momentum cancels and you get 0. But the X momentum will be what it is. They have nothing to do with it. Okay? So when these things are tested, it is critical that you make sure you break it into components. Write yourself a little star if you have to, and make sure that you know that. So Pxi equals Pxf. And Pyi, well, let's say the sum. Let's use K's here. I sum P, Y, K, F. Okay? So this is the system momentum on the way in, system momentum way out in the two actual directions. It's not hard to do. You take the components in advance like we did with navigation questions or anything else. There's nothing new here at all when it comes to that. And you can work it out. Now what you can do with some of these is you can take one of the work problems in the textbook as an example, And you can forget the answer, just grab the question, sit down and play with it, pursuant to these instructions here, and you'll find that it goes pretty well. And you know what's happening next year. I just want to make sure that's okay. That's okay. Okay, now I want to go back a little bit to the beginning. Collisions microscopically. We use conservation of momentum because collisions happen rapidly. And this way we can, I'm hearing noises. We okay? Oh, it's Ethan has his microphone on. Can you turn it off, son, if you don't need it? I hear you typing. So this can happen rapidly. So, and by using momentum, we can take and analyze very stable initial conditions and final conditions. No fancy equipment required. In truth, a collision is the compressing of a quote spring with a very high K value for a certain amount of time. So you will see something like this, integral of f dt. This is from t1 to t2. And so what we'll have is two momentums from the initial time, and this creates a delta momentum, a change in momentum. And we know that this as impulse. And the symbol for it is J. And often the first time is 0. So we are really calculating the momentum, but we're basically saying it had no momentum at all, and now it has a lot of momentum. Okay, excuse me. Hello. Just put them there, my dear. I'm on the air here. Thank you. Miss Wood says hello. 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 Okay. And so when we do the simulation, which I'm going to talk a bit about, and when my web page surfaces, we can look at it in bigger detail. The simulations always work from the simplest concepts. We don't make assumptions such as momentum is conserved or anything like this. We work from the simplest things and do them over and over and over again. If that simple basic event is correct, then all these other things will happen anyway. So a simulation, and this is distinct from a rendering, okay, is a computation where the n+1th value is dependent on the nth value. Now, if a particular simulation is known and isn't going to change, sometimes we can do least squares or some other type of curve fitting to it to know if we're on the track. But there isn't a function that can position us on the track with true, how would I put this? The simulation is so complicated, the actual calculation, that the only easy way to do it is to really do thousands of steps. And instead of just having one big equation. Big equation typically is a rendering, where you just kind of know what's going to happen, and you draw a rectangle or something. But in this case, if we launch, or we talked last time, so I'll just use that, we launch a rocket. Okay, so what do we have here? We have mass dropping off really fast, the thing's speeding up, so it's picking up drag, the atmospheric density is decreasing as a function of the logarithm of the altitude, more or less, etc. Not to mention messing around with the engines themselves, going from subsonic to supersonic, and the drag effects that it creates, and all the rest. So this is a pretty hideous set of circumstances. The equation, if you did be able to solve it, would be as long as your arm. So instead, we solve a whole bunch of simple equations repeatedly, and none of them are that difficult. And we take the mindless, numbing, crunching capability of a computer to just keep going through the loop. And that's what you'll be doing. So a simulation uses the basic concepts over a brief instant of time. We'll just call that delta t, adds them on, and then moves the clock ahead another interval, and redoes the computations. Again and again. Now, this wasn't possible until we had computers, decent ones, and the ability to fly spacecraft into orbit and so forth really requires this. To train astronauts requires this. You can't say, I want to learn how to fly, I'm going to go flying in a Cessna 150 with my instructor and watch him or her fly the plane and learn what to do for $150 an hour or whatever. An astronaut spacecraft, the flight is way too expensive and way too complicated and all the rest of it. We can't fly 50 missions just so we can train the astronauts. And the spacecraft, especially in the old days, were not automated in any way. We watched, for example, the Dragon flight there earlier this year, and the fellas didn't do very much at all. But in the old days, they were doing everything, pretty much. But we needed those guidance systems to keep the spacecraft going. And for example, when we went to Jupiter in the Voyager spacecraft with the gravity assist situation in 1979, 1980, they also not only just want to get to Jupiter, you want to look at the moons of Jupiter. And you want a path that goes through there that can pick off as many of those moons in such a way based on timing and situation. And my understanding is they flew about 4,000 simulations. And at that time, you would be using pretty big computers at NASA to run all those numbers, because you'd be having very precise values and probably some significant digits there, so that you could really manipulate the spacecraft. In addition, you have your spacecraft's an engineering piece of equipment. So on top of that, that thing is going to fly, and then it's not going to be exactly correct. Its rocket engines will perform slightly different. There'll be some little subtlety to it, and you're going to have to bring it back. And so there's going to be constant sense of, okay, here's where we should be. Are we there? Are we somewhere else? How do we get back to the optimum pathway? And on it goes. So there's really without the computer to do it. So I like to show you that by making you write simulations for the collision of two objects that are both moving towards each other, perhaps, and there's a glancing collision in 2D. And it's a very difficult algebraic question to solve. And so when my page wakes up, we can go through that. And this is a good time for us to work out. And so this is kind of like a first lab, if you will, for you folks. So you can organize yourselves into, and I don't care which class, it doesn't have to be this one or well, you're both together today anyway, A or B, makes no difference to me, you're all my children. And we've got, let me see officially today, but half of them are probably not true. 22 or 23, so there's probably 6 groups, I guess, roughly, but you people know better than I, so we'll just figure it out. And what I'm going to do, also I told you last time with stress balls, so what I'm going to try and do is come up with some kind of way to give you some randomized spring coefficients and so forth, so that we don't all get the exact same results, because that's boring. Okay, so this is, so as soon as my web page wakes up, you can go and have a look. If it isn't, I'll check, make sure it's there. I can't remember if I woke up the lab manual or not, but we'll put that up and you can stare at that. It gives very specifics about how to submit this, so whoever's in your group who pays attention to those details, please make sure you do that, because marking this kind of thing is really brutal, and it doesn't serve you for me to be wasting my time flipping around trying to find stuff. So you do whatever you're going to do, but there's summary aspects that you have to do with the paper so that I can do it. This is not done in AP Physics format. This is, you know, just simply neatly presented. Okay, it doesn't have to be a big fancy deal. And again, remember, manage your workload. If it says photocopy a sample problem, don't write it out. Just do what they say, because you're busy. Okay, and it's great to work hard, but make sure you're working hard doing the right things. The things you put your time into are meaningful and directed. Okay. Yes. Hello, please.
What's a glancing collision?
Oh, okay. So that's where. Okay. Thank you. Let me just find. This will work. I got 2 pieces of masking tape here. Okay. So head-on collision, right? But a glancing collision would be where, let's say this is at rest, and I hit it at an angle. So it's not a straight-on hit. When I hit it on an angle, they're going to deflect like this, right? So in some way. So that's what we call a glancing collision, which is what I was trying to encourage you to do, were you to be in a situation of the car, because when that happens, there's going to be a lot more time, and hence displacement, to slow down, even though you've damaged your car and you're sad. It's way better than being dead. Okay? And you know the physics now to be careful of those things. And that's the same thing with other activities too. You know, going swimming at the cottage or something or wherever, you don't dive in head first into water that you don't know. There's just a rock there, that's the last thing you're going to do. You get in the water, you be careful. If you do jump off a big rock somewhere, you make damn sure you know in advance that underneath there's 20 feet of water. All right, you don't be doing things, even though you're with chums and you're being goofy or whatever. The problem is that these types of things are critical and do not care about your state of mind. The laws of physics aren't interested. I think I mentioned last year briefly, but I'll just bring it up. The Princess Diane accident, which is now going on 23 years. At the time, it was a shocking event. She was one of the most popular women in the world at the time. I think it's a fair thing to say. The media hung on everything she did and said. We didn't say too much, but what she did, and she was pretty, and of course she had been married to Prince Charles, and that didn't work well, and she was off with another fellow and so on, and the press would hound her because the people would buy the magazines with the pictures in them. So she gets in a car with the fellow. They take off. It's a high-powered Mercedes, and he goes into a tunnel in Paris. And what we think happened was there was a car came alongside and took a picture inside the car, trying to get them inside. And of course, the flash bulb was probably caught the driver by surprise. It would probably cost many of us, especially if you're driving very fast. So he hit the wall of the tunnel, and then because of that, he glanced at the wall tunnel and went across and hit one of the pillars. And when he did that, the entire car stopped within about 30 centimeters. Princess Diana and her partner, or friend or whatever, were not wearing seatbelts. This is often the case with wealthy people. And so they bounced around in there pretty badly. And he was cut bad enough that he died in the car. She hit hard enough, apparently, that her heart moved to the other side of her chest. So this, you can just imagine the damage. And in France, at least at the time, my understanding is that their first aid system was they tried to work on the person at the scene of the accident instead of throwing them in the ambulance and getting to the hospital as quick as possible. That their philosophy, not right or wrong, was to deal with it right at the scene, and that would buy them the extra 10 or 15 minutes of how long it takes to get to the hospital. Whatever the reason, it wasn't successful, and she didn't make it. So it was a disaster. It was one of the more profound funerals in England's history. And this whole idea of putting flowers at the base of some location, in my view, pretty much started with the death of Princess Diana, which just seemed to shock the nation. But this is the whole situation. You have this incredibly well-made, highly expensive, very well-engineered car, and it hits a pillar, and you don't have any stopping distance, and there's a point where it just can't help the people inside. And that's also why personal restraints may well have been useful too. It's hard to say whether they survived or not. I don't know. But either way, it was you know, I mean, I don't wish what she didn't really make much difference to me, but I certainly don't wish that poor woman any difficulty. But that's a long time ago now. All right, I guess we're at 3:15. I think you've had enough of me, probably. Any more questions?